In this lecture, I'll talk about frequency distributions. This may be something that you're familiar with, others may not be, so I just kind of take the stance that everybody's on the same playing field, there were no prerequisites, and we don't have any clue what frequency distributions are. We'll talk about the frequency tables and the histograms, and then other shapes of distributions. First, I would like to talk about data and how we gather data and what it looks like when we store it in our computer. We'll talk more about this when we introduce SPSS, but for now, let's just talk about this simple spreadsheet that you see. Data are collected and stored in what we call spreadsheets. So here, each row represents a subject, so my data set has 5 subjects, and each column represents a different variable. So here I have 2 variables, gender and age. For the first person, we see gender 2 and age 25. Non-numerical data for categorical variables like gender, we often code in our spreadsheets. And it's important that we remember how we code them. So we have male equal 1 and female equal 2. So this first person is a male aged 25. The fourth person is a female aged 27. And then we can take this spreadsheet and summarize the data with frequencies and descriptives. A frequency table organizes discrete data indicating the frequency or how often each value occurs. So here on the bottom is our frequency table for the variable gender. Each value of gender is listed in one column. So here my levels of gender are male and female. And then the frequency is the number of males. We have 3 of them. And the number of females, we see 2 of them within each of those levels. The categorical data can be displayed with a bar chart. Now you may think this also looks like a histogram. Is this the same as a histogram? It's not quite the same, but I'll talk about the histogram in just a moment. For now, we'll stick with a bar chart for categorical variables. On the x-axis here, we see the different levels of our variable, male and female. And on the y-axis, we see the frequency of the observations. So male had a frequency of 3, and the bar height is 3. Female had 2 frequency, and the bar height is 2. Now notice for this bar chart that the bars do not touch. So that's one of the technicalities of a bar chart, but you don't often see it whenever you see bar charts or histograms and the differences in actual publications. A grouped frequency table is for continuous data. So our gender was categorical, and for that we used a bar chart. Our age is continuous, so for that we're going to use a grouped frequency table. Now this data isn't too bad, but if we didn't group them, then we would have to have a bar at 22, a bar at 24, a bar at 25, 27, 30, and so what this would look like is just a x-axis with one frequency for 22 and a big space. There's no 23, there's no 24, there's 125, so we would see another bar there. But that's not very helpful for us, especially think of a variable that has a very wide range, like income, that might span from 0 to 100,000. We don't want the x-axis to have 0, 1, 2, 3, all the way up to 100,000. So we group our values into smaller equal interval ranges. And there are different rules that people go by on these ranges, but it's really up to you. So I've taken age and I've broken it up into 4 subgroups: 20 to 22, 23 to 25, 26 to 28, and 29 to 31. Now it is important that each of these is an equal interval. So here we have a range of 3, of 3, of 3 values, and of 3 values. Now our frequency is the number of observations within each of those ranges. So we have 25, 22, 30, 27, and 24. So the frequency within each of those is 1, 2, 1, and 1. For continuous data or numerical data, we use a histogram. It looks like a bar chart. It's made up of many bars, but notice now they're touching, so there's not any space to indicate the continuity of the continuous variables. On the x-axis, we have age, but instead of each individual age, we have the midpoint of the different groupings. So the midpoint of 20 to 22 is 21. The midpoint of 23 to 25 is 24. So those are the levels that you see here on the x-axis. And then each bar is centered over the midpoint at the height of the frequency. A line graph is similar to a histogram, except instead of bars, we just use a bunch of lines. Some might call this a frequency polygon. Again, we have the midpoints of our grouped frequencies, and then instead of the bars, so imagine this without the bars, but I wanted to give you the visual, we just put dots on top of the midpoints, or centered over the midpoints, and connect the dots. When we talk about shapes of distributions, notice here we have a histogram with a bunch of bars, and then over that we have laid this line. So it goes from the left all the way to the right. This is the most common distribution or shape of a graph that we can see. So a distribution is the way in which values are dispersed across the frequency table. This is the normal distribution that you might think it's the normal. We'll talk more about the normal distribution. There's a whole lecture, a whole week on the normal distribution. But some of the characteristics are bell-shaped, so it looks like a bell. It is symmetric about the center. So if we drew a line on the center and folded it in half, it would match up. And it's also unimodal. There's only one mode or value with the highest frequency. So here we could see that it's centered at 0, and then the x values, so these are the midpoints within each of these bars. So we could calculate what each of these spans. And sometimes you'll see this in a histogram form. Sometimes you'll see it in a frequency polygon or line graph form. In addition to the normal distribution, we have skewed distributions, bimodal distributions, J-shaped distributions, and rectangular or uniform distributions. Skewed distributions are those that are asymmetric. So they have many of the same characteristics of the normal distribution, except, so they have one mode here, and they're somewhat bell-shaped, but one tail extends much further than the other tail. If it extends towards the left or towards smaller values, we call it negatively skewed. And if the long tail extends in the positive direction or towards larger values, we call it positively skewed. A bimodal distribution is one that has two values on the x-axis that have the equal and highest frequencies. A J-shaped distribution, so this is what we would call a J-shape. It continually, in this case, it continually increases. So it starts at the minimum and increases up to the maximum. We could also have a J shape that started at the maximum and decreased down to the minimum. This one here, where we start at the minimum and end at the maximum, is called a ceiling effect. And the one on the right, where we start at the maximum and end at the minimum, is called a floor effect. I put up this inverted U shape. We might confuse this with a normal distribution because it has one mode, it's symmetric, there are many characteristics, but there are certain characteristics that are specific to the normal distribution that would separate it from something like this inverted U shape. The last one is a rectangular or uniform distribution where it has the same frequency for all values. So for instance, if we were looking at colors and we had brown hair, blue hair, and green hair, and we have 3 people that have brown hair, we have 3 people that have blue hair, and we have 3 people who have blonde hair. No, blonde, black, brown. It doesn't matter, I guess. But for any of those categories, there's the same number of people within those. That would be a uniform or a rectangular distribution. Here are some graphs that I've pulled, and I want you to identify the shape of each of these distributions. If we were to draw a line over self-esteem, we see that it increases and then it decreases. It has a single mode, but the left tail is much longer than the right tailed. So this one is negatively skewed. If we're looking at birth weight, we see one mode, and we also see the bell shape, and now we see symmetry, the same equidistance from the middle out to the left and to the right. So this one is normal. If we look down here at running time, this one is interesting because if we think about this being the middle, and if we went all the way out to the left and to the right, pardon my bad pen, we would think might be normal, it might be symmetric, but if we looked at this a little bit differently and we said, oh, that one's pretty far out from all the others, what we would call an outlier, if we just included the majority of the observations, then we might say that it's positively skewed. So it's important to understand the effects of our outliers in our distributions and if we want to include them or not. The last one, Americans online by age. Notice here at the bottom we have our age ranges. So instead of the midpoint, they actually put the range. And because the bars don't touch, it's still a histogram because we have a quantitative variable down here, but we have 2 bars representing 2005 and 2008. Now overall it might not be exact, but if we look at the general trend, we see that a majority or the maximum frequency occurs in the first category, and there is a continual decrease, and the minimum frequency is at the largest value. So this is one of those J effects, and because it starts at the maximum and goes down, I want you to think of some shapes of distributions for each of these different ones. I've given you some examples. So a normal might be birth weight. We just saw that in the previous histogram also. Something positively skewed might be U.S. income. There's a majority of us who make about the same within some range of values. There is this level of poverty, but then there are the Bill Gates and the Donald Trumps way out here that are pulling that tail to the right. So we would call this positively skewed. Something negatively skewed might be our cognitive ability over time. So as we age, our thinking gets better and better and better up until some mid-range age, and then for some we hit a milestone and our thinking ability decreases rapidly. So this would be negatively skewed. If you are in business and you're watching daily prices of something, perhaps milk prices for the month of January, then if you every day check on the price of milk and it happens to not change this month, then we would have a steady, constant, rectangular or uniform distribution. Another effect of a ceiling effect, a J shape with a ceiling effect, is our cumulative annual rainfall. So in January 1, we start at 0, and then as we progress through the months, cumulatively, if we're adding on the previous month, we have the total rainfall for the year in December. For the floor effect, I don't have a graph up here, but if I draw it, we think of car depreciation in most cases. When we buy it, it is the maximum value, and then as soon as we drive it and we continue to drive it, the price for it continues to decrease. That is all for frequency distributions. We've talked about how to make frequency tables, the difference in that and a grouped frequency table, and we've also talked about different distributions. If you have any questions about these terms or some of these comments, please go back and listen to other lectures. Also, remember to use the discussion boards if you have any questions regarding the content of this lecture.